Right, shall we get started? So these are all the concepts we saw yesterday, right? Go close up, speed of an electromagnetic wave, right? The speed of electromagnetic wave. E naught na? E naught na? What is E naught? Forgot in one day. Correct? So E naught is the magnitude of the amplitude of the electric field, and B naught is the amplitude of the magnetic field. Right? Also, you can write it as E divided by B. Is that right? So, did you observe in yesterday's problem, though I gave you the formula as E naught by B naught, but in yesterday's problem, we used it as E by B. Why? How can both be the same? Because if E vector is written as E naught sine of kx minus omega t, and B vector is written as B naught sine of kx minus omega t, what is magnitude of E vector? If I take magnitude of E vector, it will be E naught sine of kx minus omega t. Magnitude of B vector is B naught sine kx minus omega t. Is that right? Correct? So when I divide both, this will get cancelled. So in that case, I can say magnitude of E naught by B naught is the same as the magnitude of E by B also. That is why we used it in the problem yesterday. I thought somebody will ask this question. You remember the problem that 6.3 J cap something was there, no? If you see, I didn't use E naught by B naught. I used E by B. Is that clear? Shall we proceed with the next topic? Yes. So now we are supposed to see what is the source of an EM wave. So what is the source of an electromagnetic wave? So first, we need to understand what an EM wave is. What is an EM wave? Yesterday we discussed it. It is a time-varying electric and magnetic fields which are mutually perpendicular
to each other as well as the direction of propagation.
That's right. So as well as the direction of the propagation. Is that right? So listen. Here, the most important point that you need to concentrate upon is the time varying. Means electric field and magnetic field are supposed to be functions of time. That is most important. Okay. So, but if you recollect the fact of where is an electric field getting generated from? If I ask you what is the source of an electric field, what will you say? So, source of an electric field is a charged particle. So if I say a particle is having a charge associated with it, then I can define electric field due to it. But the important question that we need to ask is, how is the charged particle supposed to be? How do you say? In the first chapter, when I discussed electric, it can be stationary or it can be in motion. But if there is a charged particle existing, there is going to be electric field. Is there any doubt in that? Okay. Now the question is, when I have the charged particle at rest. So when I have the charged particle at rest, what will get generated? So if I prepare a table, okay, if I prepare a table, electric field and magnetic field, is electric field getting generated? Yes. What about the magnetic field?
No.
Why? Because for magnetic field, charged particles are supposed to be in motion. What is the source of magnetic field? Moving charges. chapter name moving charges and magnetism, right? One more thing is this electric field is there, right? The electric field that is getting generated, is it going to be constant or a variable at a given location? It will be it will be a constant electric field. I'm not saying it is uniform electric field. There is a difference. So it is constant at a given point. Are you in acceptance with this? Are you able to understand what I'm trying to say? So if I take a charged particle like this, the isolated charged particle, if I take the location P, which is at a distance R with respect to the charged particle, at this point P, is the electric field going to change with respect to time, or is it constant everywhere? It is not a function
Constant,
of time.
sir.
So can a charged particle at rest generate an electromagnetic wave? Definitely not. Why? Because an electromagnetic wave is a time varying signal. But how can you generate a constant signal? So obviously not possible. Is it clear? Secondly, I'll put the charged particle in motion. Whereas when I talk about motion, I can talk about two types again. One is uniform motion, and the second is non-uniform motion. Am I right? Is it right? So when I talk about motion, especially when I say that there is a charged particle in uniform motion, when you see the word uniform motion, what comes to your mind? Velocity of the particle is a constant. So when the velocity of the particle is going to be a constant, can I say that there is a uniform current that is getting generated? So when there is a uniform current that is going to get generated, it will generate magnetic field for sure. But what will happen is, in this case also, electric field and magnetic field are not going or not time varying. They will not be time varying because both are under uniform condition. Right? So what should you do to the charged particle? You should not move it with uniform velocity, rather give it an acceleration. So to give it an acceleration, what you can do is you can put the charged particle into oscillation. Means how do you make the particle accelerate? Accelerate in the sense you will not take the charged particle and make it move in a straight line path. Rather, you can make it oscillate. Because you remember in oscillations, every particle has acceleration. Subrajit, what is the acceleration possessed by a particle in oscillation? A is equal to minus, you're almost there, omega is correct. A is equal to minus omega square A or X. A is equal to minus omega square X. Do you remember this? At least you remember seeing this kind of an expression, A is equal to minus omega square X in simple harmonic motion. Means every particle which is oscillating at a given point will have this amount of acceleration. The minus sign here indicates that the acceleration is always directed towards the mean position. Mean position. Or charge particle if it is oscillating. So let's say this is the mean position. M is the mean position. If the charge particle is at point P, though the particle is moving in the rightward direction, it will experience an acceleration in the reverse direction. That is why there is a minus sign. So if this distance is x, so if the particle is having a displacement in this x direction, it will have an acceleration in the negative x direction. Is the point clear? These are all the concepts of simple harmonic motion. So when this kind of a scenario happens with respect to a charged particle itself, means if I'm able to take a charged particle and put it in oscillation, it starts accelerating. And what will happen is this oscillating charged particle will start creating a time varying electric field, which in turn will generate time varying magnetic field, and the vice versa. So one will create another and the other will start creating the reverse of it. As a result of which, you will have an electromagnetic wave getting generated. Okay, nobody will ask you the story and all, but for you to understand. The question that you can get in your exam is, what is the source of an electromagnetic wave? Your job is very simple. Oscillating charged particle or a charged particle under acceleration, or an accelerating charged particle. Is that clear? Shall we proceed? Is there any doubt till what we discussed? Is it clear? So the topic that we discussed previously is called as source of an electromagnetic wave. Clear? Which part? Rest. Yeah, when the charged particle is at rest, there will be an electric field that is getting generated, which is constant at a given point. Electromagnetic field. Electric and magnetic fields together, both are almost the same. But generally, we don't call it as electromagnetic field. We either call it as electric field or magnetic field. Electromagnetic waves, generally we call it. Okay, why we call it as waves? See, more technically, as a science student, you should use the word wave. Here and there, people use fields also. If you've seen movies and all, they use field. Not sure if you have seen Robo movie. I watched Robo movie, Rajnikant's movie. How many of you have not watched? This 2.0, when they use it, no, they go to the tower with that machine in hand. You remember? They'll start sensing the electromagnetic field, and then they call it. Okay, field in Yesulana because it's a region. So if the electromagnetic waves are existing in a region, we call it as electromagnetic field. But more technically, we should call it as waves because they're mostly used to transmit energy from one point to another. Breathe. Shall I proceed? Right. So there is a reason why we discuss this topic, because here there is another point that I need to mention. So when I put a charged particle in oscillation, I repeat, when I put a charged particle in oscillation, can I say there is a frequency associated with it? So an oscillating charged particle has a frequency associated with it, right? And what will this value of frequency get corresponded to? The frequency with which the charged particle is oscillating is exactly equal to the frequency of EM wave that is generated. So if you want to generate a frequency, if you want to generate an electromagnetic wave of a specified frequency, what are you supposed to do? Take a charged particle, put it into oscillation of that particular frequency. Okay, but it is not as simple as we speak. It's theoretically spoken, but there are a lot of machines and all other things that have to be maintained for these kind of waves to get generated. But there are some hazardous waves as well, which will affect us if not handled properly. Okay. So since we understood the fact that a particle with a certain frequency in oscillation can generate an electromagnetic wave, what they did is, so before I proceed, right, are you in acceptance with the fact that a wave which has a frequency will obviously have a wavelength also associated with it? So waves have frequency, and waves obviously have wavelength. Name itself is telling you length of the wave, right? So they have it. So based on the wavelength and frequency, the electromagnetic waves are classified into different bands, which we they are classified into different bands. Okay, and each band forms a part of, I can call a symbolic representation called as electromagnetic spectrum, which I'm sure you would have learned in your chemistry. In your atomic structure, you would have learned about electromagnetic spectrum. But maybe at that point, you would have not known what is the reason for it and all those things. Is that right? So the question of this electromagnetic spectrum comes due to this fact. Okay. I'll tell you how these chapters are connected. So one is, okay, you understood that electric field and magnetic field, you know the sources of them. If you see the electromagnetic waves, one of the main applications of them is in the communication systems. We're using mobile phones and everything, right? Wi-Fi, all these things, all wireless devices are there. So you need the signal to get carried from one place to another. You have different kinds of transmission methods, right? So those are all learned under communication. Communication system is actually the 15th chapter of your book, which is deleted. Okay. So I'm trying to say that one of the applications is there. And secondly, when you learned about this electromagnetic spectrum, right, it has something to do with excitation and de-excitation of electron when it moves between different orbits. You remember the concept of Bohr's theory? Do you remember the concept of Bohr's atomic model? Do you remember or not? What does it speak about? You will be learning about this year also. But if I tell you here, you will be able to connect it there better. So orbits have fixed energy means who proposed a model before Bohr? Between them, there is one scientist. Alpha ray scattering experiment is there. Rutherford, so he proposed about the nucleus and all those things. So he also told that electrons can revolve in circular orbits. But the mistake he made is, he didn't say they can revolve in circular orbits. He told they can revolve in any random circular orbits, which was not possible. Okay. But Bohr was the one who corrected, saying they are supposed to revolve in those orbits where the energy is quantized. Stationary orbits and so on. You've heard of that, right? Stationary orbits. So if I say this has one orbit, this has another orbit. If an electron, if for an hydrogen atom, which has one electron, right? If that electron is in excited state, when I say excited state, what should happen? The electron definitely should not be present in the first orbit. Let's say it is present in the second orbit. And from the second orbit, it is getting de-excited and jumping to the first orbit. So whenever this kind of a scenario happens, energy is released. Okay. Energy is released. And how is this energy released? In the form of EM waves. Based on this, you would have learned about these series, different kinds of series. Do you remember? So what happens when an electron jumps from higher orbit to the first orbit? What series do you get? You get a series called Lyman series. You remember this? So in Lyman series, the electromagnetic waves that are getting released correspond to which band or which part of the electromagnetic spectrum? Infrared at the 3. This is ultraviolet. So ultraviolet, the wavelengths that are getting released will be corresponding to ultraviolet waves. Okay. Similarly, when it jumps from any higher orbit to the second orbit, what series is there? So they have Balmer series, and Balmer series corresponds to inner light, visible light. So this visible light, you already know the wavelengths and other things. So what are the wavelengths? Last year dispersion of படிச்சீங்க. Oh, that's 10th standard, yes. So where does the wavelength range from? 400 nanometer to, you remember this? So visible light corresponds to these wavelengths. So what I'm trying to say is, based on, instead of you remembering everything as a single wave, okay, what they did is they broke it into chunks depending on the different kinds of applications they have. Okay. So depending on the applications that they have, they are broken into different bands. Okay, where certain bands might overlap also. புரியுதா நான் சொல்றது? So you have still more that we'll discuss in atomic structure. The other three are corresponding to infrared region. Okay. Those who are online, I hope you're able to understand. Yes or no? Okay. So this is the electromagnetic spectrum I'm trying to talk about. Clear? So you have seen this, right? Yes or no? Yes or no? Yes. Okay. So when you talk about the frequencies are written from top to bottom in the ascending order, whereas the wavelengths are written in the descending order, from bottom to top when you go. Okay. So they are written in the reverse order. Now listen. So depending on what charge particle is put into oscillation, I repeat, depending on what charge particle is put into oscillation and what frequency is getting generated, they are classified into different segments. What are they? First is you have, what are you able to see? Radio waves. Then you have microwaves. Then you have infrared. So above infrared you have visible. Above visible you have ultraviolet. Above ultraviolet you have X-rays, and above X-rays you have gamma rays. So this is the increasing order of frequency. When I say increasing order of frequency, can I say increasing order of energy also? Sollalama illaya? Why? Because E is equal to h nu. You remember this? So energy is directly proportional to frequency. Or this can also be written as hc by lambda. This is the Planck's equation of energy. So what do we say? Energy is increased if the frequency is increased, and energy is increased if the wavelength is decreased. So in both the contexts, if you see on either of the sides, they make sense. Okay, where wavelength is measured in terms of meter and frequency is measured in terms of hertz. Is this point clear? Okay. Next is, if you see radio waves itself, radio waves are again subclassified into different types. What are they? You have long radio waves, then you have AM radio, then you have television and FM radio, then you have short radio waves. So all these long and short are decided by the wavelengths. Okay. So long radio waves obviously have more wavelength. You're able to see them here. What is AM base? Any idea about what is AM? AM. Okay, at least you listen to FM, right? What is FM? Frequency modulation. So A means what? Just amplitude modulation. That's it. So I think I remember explaining you what is modulation. So what is modulation? You have a message signal. When that message signal is mixed with a high frequency signal, that is a carrier signal, then you get, and then you say that the wave is modulated. Right. In FM, frequency is modulated. Frequency of the carrier signal is modulated. In AM, amplitude of the carrier signal is modulated. Similarly, you have something called as PM also, which is phase modulation. Okay. Is it clear, guys? Right. The next is you have television and FM radio. See, I'll just give you the outline of this part. I'll tell you how to prepare your own notes. Okay, there is nothing for me to teach in this. It is just all about knowing the values and you writing the exam. I'll tell you what kind of questions will be asked. Okay. See, for example, if I take radio waves are a part of, they're a part of EM waves without a doubt. Is that right? So, but just now we saw the fact that EM waves are generated using an accelerated charged particle. So for you to have radio waves also you need to put an accelerate, you need to put the charged particle in acceleration. But what is the specific type of particle which is accelerated? And how are they accelerated? Radio waves are produced by accelerated motion of charges, no doubt in that. But where is it done? In conducting wires. So what I'm trying to tell you here is, they will ask you a question like this. Tell me the frequency range of those electromagnetic waves which are getting generated due to acceleration of charged particles in conducting wires. I repeat the question, listen to this. Tell me the frequency range. Okay, give the frequency range of the electromagnetic wave which is produced by accelerated charged particles in conducting wires. First of all, what is that you're supposed to know? First, you need to know that they are radio waves. And for radio waves, you have a specific set of frequency range associated. So that range you need to prepare. Or they can ask a question like this. Give two applications of electromagnetic wave which is generated by charged particle in conducting wires. Means indirectly they are asking you, give two applications of radio waves. Yes. Question frame up. I gave you a question. How is it framed? Give to application of. What did I tell? Give to application of EM waves which are generated by the accelerated charged particles inside a conducting wire. Similarly, if you take microwaves, right? Then microwaves are produced by special vacuum tubes called klystrons, magnetrons, or gun diodes. So these are all the devices that are used. Okay. So what you need to do is you need to prepare a table like this. You need to prepare a table like this where you have different kinds of waves, EM waves that are associated and their wavelength range. Only additional part that I would say is prepare a table for frequency range also. Okay. And you see how are they produced. You need to write down. Okay. After that, you also write down how are they detected. So how do you detect radio waves? See, for example, if you look at FM and all, you will have an antenna on top of your car. So antenna is the receiver axis. So they detected using the aerials. Aerials or antennas, they both mean the same. Okay. Similarly, how are microwaves detected? You have something called as point contact diodes. So you first prepare the table for all these things, and the questions will be based on this one. Is the point clear? Mostly, they might not ask you the range and frequency. They will say, give an application of an electromagnetic wave whose frequency range is this value. Upon the, you should know which wave it corresponds to, then only you can mention the use. So in this chapter, mostly the questions are based on this point only. Problems are actually less. Okay, but mostly they ask only from this data set. Is that clear? So you need to make a note of this point. Next is, the next point is, what is the total energy associated with an EM wave? So what is the total energy associated with an EM wave? So for that, energy in the form of electric field is going to be that. Actually, you are speaking about energy density. Okay, I would rather make it as total energy density. Okay, So what is UE? What is the energy density in terms of electric field? Half do you remember this expression? Yes or no? See, in capacitors, we derived this. No? In capacitor, what is the energy? U is equal to half CV square, where V is the potential source, potential difference. So half into epsilon naught A divided by D into, how can you write V as? V is equal to E divided by D. So E is V by D, sorry, E is V by D. So it will be E into D square. Okay. So epsilon naught A divided by 2D into E square D square. D and D will get cancelled. Half. So epsilon naught A E square into D. So this is the energy. But what do we want? We want the energy density. So energy by volume. So what is the volume of a parallel plate capacitor? A into D. So A and A are gone, D and D are gone. So we are left out with half epsilon naught E square. Okay, this is the energy density. Let me call this as equation number 1. So what is the other field that is present in it? Magnetic field. So what is the value of magnetic field? Half. Replace electric field with magnetic field. So B square divided by, you replace epsilon naught with 1 by mu naught. Divided by mu naught. Let this be 2. So what is going to be the total energy density? UE plus UB. So how much is that value going to be? Half epsilon naught E square plus half is that right? I'll write it again. Listen. See. Half epsilon naught E square plus half into B square divided by mu naught. Okay. When I have this value, listen to this. What is the relation between electric field? Okay. What is the relation between mu naught and epsilon naught? C is equal to 1 divided by root of mu naught into epsilon naught. This we saw yesterday. Similarly, C is equal to E divided by B. Right? So what I will do is, I'll convert epsilon naught in terms of mu naught and I'll convert electric field in terms of magnetic field. Can I do that? So half into, in the place of epsilon naught, what should I write? C square into mu naught is 1 by epsilon naught. No? Then epsilon naught is 1 by mu naught C square. Correct? So half into 1 by mu naught C square into, what is the value of E in terms of magnetic field? E is equal to C into B. So C square. Oh, sorry, wait. One by mu naught C square. This is C square B square, correct? Plus B square divided by 2 mu naught. So what will get cancelled in the first term? C square is gone. So this will be B square divided by 2 mu naught plus B square divided by 2 mu naught. So what is this energy? What is this value going to give you? It will give you B square divided by mu naught. Is it clear? So this is going to be the total energy associated with an electromagnetic wave. In a similar way, guys, is there anyone having doubt in this?
No, sir.
No. You not see square. step. So here I did no. C is 1 by root mu naught into epsilon naught that I gave you yesterday itself. Okay. So square on both the sides. C square mu naught is 1 by epsilon naught. Rearrange the equation, you will get it. That's what you will have to do next. Right? Then that's what you will get. So total energy, what is that you got? B square divided by mu naught. So let this be star. Similarly, can I write B in terms of E? Can I? So again, we know that C is equal to E by B. Then what is B? E by C. Similarly, C is equal to 1 by root of mu naught into epsilon naught. So what is mu naught? 1 by epsilon naught C square. Is it right? Is it right? So what should I do to this B? Substitute it here. So this will be E square divided by C square, the whole divided by mu naught. Or else I'll write it like this. 1 minute. Can I write this as E square divided by C square, the whole divided by mu naught? How can I write it? Mu naught is 1 by epsilon naught C square. So C square and C square will get cancelled. So what is that you're left out with? Epsilon naught E square. So from this, if you observe, when you calculate the total energy density, so when you calculate the total energy density, you either get P square divided by mu naught or epsilon naught E square. Is it right? Here's what happens. Is the point clear, guys? Then electric fields. Because basically electromagnetic waves have the speed of light in vacuum, right? So that is why they depend only on these 4 parameters. What are they? Electric field, magnetic field, or permittivity of free space or permeability of free space. There it is. It should change as mu. Which one? But the speed of light will change in different medium, right? Speed will change. So there is one important point you need to have in your mind. When you talk about an electromagnetic wave, it has a frequency associated, right? Frequency is a parameter that will not change with medium. Any idea? I repeat it. Frequency, so you would have learned this in your lower grades, right? When light travels from one medium to another, what happens to it? It undergoes refraction. So what are all the parameters associated with light? It has speed, it has wavelength, and it has frequency. So when light travels from one medium to another, I accept the fact that it undergoes refraction. But why is refraction happening? What parameter out of these 3 things are changing for the refraction to occur? So it is speed and wavelength that is changing. Then why are you saying frequency is not changing? How can you conclude the fact that light, when it travels from one medium to another, its frequency does not change? This is also another important question. Please make a note of it. When light travels from one medium to another, just make it as a note. When light travels from one medium to another, its frequency does not change. Its frequency does not change. Why is it so? I'll give you a hint. It depends on the topic that we discussed today, the first topic that we discussed today. So at the end of the first topic, what is the point I gave? other part notes answer. What did I tell? First point and everything discussed. What did we discuss today? Source of an electromagnetic wave. In source of an electromagnetic wave, what is the last point I gave? Frequency of the electromagnetic wave is decided by the frequency with which the charged particle is oscillating. Means the charged particle has generated a frequency, right? That is the frequency with which the wave will travel. So that frequency has nothing to do with the medium in which it is traveling. It only depends on what is the frequency of the oscillating charged particle. So this is an often asked question. Okay, so mark it as important. They'll ask you why does the frequency not change when light travels from one medium to another? Write down the answer below that. This is a keyword they expect. Frequency is the characteristic of the source. Frequency is the characteristic of the source. Frequency is the characteristic of the source. What is the meaning of it? Means frequency of electromagnetic wave depends only on the source that is producing it. It does not depend on in which medium it is traveling. So if you connect all the dots, the question you asked is, when you calculated the total energy, are you trying to say that it depends only on these 4 parameters? Yes, they do. Because, see, when light travels from one medium to another, what parameter will change here? So observe that. When will you write mu naught and epsilon naught? When will you put that naught in physics? When you talk about vacuum or air or free space, whatever you call it, right? So that mu naught and epsilon naught, when the medium is changed, what will happen to them as well? They will also get changed. Where mu naught will become mu and epsilon naught will become epsilon. Okay. So his question was, when it is going to travel, are the parameters going to change? So what parameters will change when it travels from one medium to another? Speed will change and wavelength will change, but frequency will not change. Okay. So we are almost done with this chapter. Yeah, that is why I wrote it as E. I didn't write it as E naught. Okay. Okay. We are almost done with this chapter, except one concept, that is called as displacement current. Okay. So before I explain the displacement current, one concept that you need to revise and come is have a clarity of Ampere's circuital law from electromagnetic induction chapter. You need to recollect, from moving charges and magnetism. Okay. And this displacement current has to speak about something related to a capacitor as well. So these are the two concepts which you need to revise and come before we discuss this, and it will take some time. We have only 5 minutes. I don't think we can complete it today. Okay. One point I want to clarify. Are you guys clear with what you're supposed to do with the electromagnetic spectrum? There is no doubt. No? That is the only topic I've given it as self-study. Because as I told you, there is nothing for me to teach. It will be boring also if I say this is the frequency. Remember, now doesn't make sense. It's better you prepare a notes out of it and start studying. Okay. Yes. So displacement current alone, what I will do is I'll maybe discuss it at the end itself. I'm saying end of the syllabus I'll discuss. I'll be a topic. Okay, it is a completely independent topic because I want to start ray optics tomorrow. Okay. So this chapter will lead you to the connection for ray optics. As I told you, ray optics is basically the chapter you learned in your 10th standard under the name called as light reflection and refraction. We'll be starting that. So I want you all to have the second volume tomorrow. Because as and when I keep doing the concepts, I'll be doing problems also. It's better you have the textbook. Is that clear? Okay. So any other doubt that you have? So prepare. If you have any doubts, reach out to me. Surya. So those who are online, any doubts, guys?
Sir,
Yeah, tell me.
sir, my doubt is not regarding this chapter. It's based on current electricity.
Okay, what is it?
Sir, for Kirchhoff's second law, if you are moving in the direction of current, then it should be taken as negative, right?
Not necessary. It is, see, whenever
Sorry.
you talk about sign convention, 1 minute, I'll come to this point. I know that there are some books in textbook and everything, they would have told moving in the direction of current is negative or positive, I don't remember. Textbook, I think they would have given it as possible. Okay. So remember one thing, wherever you are using sign convention. So you use sign convention at different places. Can you tell me where all do you use in physics? One is obviously in vectors. Yeah, you use in thermodynamics. Then we use in KVL, Kirchhoff's voltage law. Then you will be using in ray optics as well when you're solving problems based on mirror formula and lens formula. You remember, no, to some extent. I'm not asking which one is positive and all. Was it Harini that was the question?
Yes, sir.
Harini, now tell me what is your doubt?
Sir, when I asked my teacher the same doubt, she told that we should not take it to be positive because we will not get the right answer. It should be taken only as negative.
I'll tell you that. I'll tell you. See, okay, listen to this carefully. Sign convention is only logic. Okay, there are no fixed rule for sign convention. For example, if I use vectors, if I throw an object upwards, okay, so how many journeys are associated with the particle? Two. One is upward journey and the second is downward journey. So what I can do is I can take the sign convention according to my convenience. So what I will do is for upward journey, if I take upward to be positive, then by default I should take downward as negative. Means if you fix one direction to be positive, definitely the counterpart of it should exist. Now what I'm trying to say is, if I have a basic coordinate system, I just have one question. Tell me, is it always necessary that this side should be positive? Is it necessary? Actually not. But universally what we do is we follow that pattern. Okay, because universally what is understood, every textbook and every person says that this is first quadrant, second quadrant, third and fourth. Maybe if I was the inventor, if I am a left-handed person, I would have taken left side to be positive for my convenience. I would have told the whole world to follow that. But what is important here? If I take the left-hand side to be positive, I definitely need to ensure my right-hand side is negative. That is what sign convention is all about. In a similar context, there are, when you come to KVL, right, my logic is, Harini, listen to this. When you move in the direction of current, I say current flows from higher to lower potential. If you throw an object from second floor to ground floor, is that object losing energy or gaining energy? So here you can ask me, which energy are you trying to talk about, sir? Here itself contradiction starts. So when I say the top floor is considered to be my reference point, when I throw the object down, now I put a question, which energy is decreasing and which energy is increasing? Potential is decreasing, whereas kinetic energy is increasing. So since I'm talking about KVL, potential the word, I took potential energy into consideration. And I told that when I move from high to low, I'm losing energy. When I lose energy, what significance do you represent? That is why I took it as negative. So if I follow this kind of a pattern, then when I move from low to high, I definitely have to make it as positive. So the point where you will not get the answer is, if you take both the directions to be, you confuse with two things. If you take high to low also as negative and low to high also as negative, means high to low you take from one book, low to high you take from other book, you apply minus for both, you will never get answer. So what does sign convention tell you? If you take one of the directions to be positive, other is negative. You are free to do that. Because when you write KVL, what is the thing you have on the right hand side? I already wrote it. You have x1 minus x2 is equal to 0 is the same as minus x1 plus x2 is 0. Mathematically, they both are same. Harini, are you able to understand?
Yes, sir.
Okay, so it has nothing to do with which direction you are considering, but you need to ensure that one is taken as positive, the opposite side has to be taken to be negative. That is the convention. Okay, is that clear?
Yes, sir. Thank you, sir.
Good. Yeah. Okay. So that's it. Okay, we'll wind up and we'll see the remaining problems. Sorry, we'll start ray optics tomorrow. Have your second volume with you. So done. In the place of, it's fine because you're taking only magnitude. Clear? We'll wind up.